Section 3.1, measures of center. So we call it measure of central tendency. There are three things here in this section. The mean or the average or the arithmetic mean. There is a median, which is the middle, and the mode. Sometimes it's better to use mean than the other one, sometimes the mode, sometimes the median. So first we start with the mean. What is the mean? To find the mean, you add all the given numbers, sum all the observations, divided by how many observations there are. There's like n of them. So you divide by n, the number of observations. That's what the mean or average or arithmetic mean. So for example, if we have a data with entries 20, 26, 40, 36, 23, 40, 35, 24, and 30. So if we have this and we need to find the mean, so all you have to do, add these numbers up, 20 plus 26 plus 40 plus 36 plus 23 plus 40 plus 35 plus 24 plus 30 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. If you do the calculations, you can use the calculator for that, you get 30.5. That's the mean. One thing about the mean, we will come back to it, like how we use it, where do we use it, and what affects the mean in a minute. The next one is the median. So the median is the middle number in the data. So when we talk about the median, what we need to do, the first thing, arrange the data in ascending order and then find the median from there. So let's say if we have this example 8, 2, 3, 1, 7, 11, 15. So the first thing we do is arrange it in ascending. 1 goes first, then 2, then 3, then 7, then 8, 11, and 15. So I crossed them out, make sure I did not miss any. Which one is the middle number? This is the middle, that's the median. Median is 7. Now, what about if the data set is, if I take the same example, 8, 2, 3, 1, 7, 11, 15, I add another one, say 9. So I would arrange it again, 1, 3, 7, 8, 9, 11, 15. There's no middle value here because there's 1, 2, 3, 4, 5, 6, 7, 8 of them. So there's 3 here, 3 there, there's 2 in the middle. So what do we do in this case? To find the median, we average means the mean, the average the middle 2 values. So this means you add the middle 2 values and divide by 2. 15 divided by 2, 7.5. That would be the median. Now if I take the same data and try to work it out here on the side, 1, 2, 3, 7, 8, 11, and 15. So we agreed that we just found the median. The median is 7. Let's find the mean. To find the mean, we have to add the numbers up, right? Add the numbers up, as I'm doing right now, and divide how many we have. 2, 4, 6, 7. Divide by 7. So it's about 6.7. Okay, that's the mean. Now, what I'm going to do here, I'm going to change the last number, let's say, into 55. Okay, what's going to happen? Now in green, I'm going to write the median is going to stay the same. It does not affect the median. What happened to the mean? Well, let's try to calculate the mean, see what happened. We add them up and then divide by 2, 4, 6, 7 values. So the mean now is 12.4. So notice what happened. If we take or change one of the observations, either make it so large or so small, I just made it so large, you could take one and make it some negative number, then the mean changes. So that affects the mean, but it does not affect the median. So the median stays the same. So if you replace a number in the data, like the largest number or the smallest number, by even a larger one or smaller one, the result does not affect the median, but it does affect the mean. It does affect the mean. It either increases the mean or decreases the mean. Okay, keep that in mind. So if you're asked what affects the mean, larger values or smaller values would affect the mean, but not the median. Okay, not the median. And that number that I wrote down there, the 55, comparing to all the other data values, it's really big. So that number is called an outlier. We'll see more about this, I think, in section 3.4. It's called an outlier. The next one is the mode. The mode, I define it as the most frequent. Mode is the most frequent, is the one that occurs. Now the numbers, the stuff we have been dealing with, the mean and median, they only occur in quantitative data. So it means you have to have numbers to it. But for the mode can work in quantitative or qualitative data. So in either one you can find the mode. The mode is the most frequent one. So let's say I have a data 5, 2, 3, 7, 11, 13, 2, 8. So which one is the most frequent? Here is the 2. So the mode is 2. What about if we have 1, 11, 13, 17, 1, 21, 5, 13? Well, here I see 1 is being repeated twice. Oh, 13 as well. So that's called bimodal. So the mode is going to be 1 and 13, bimodal. So a data can have more than one mode. And if nothing repeats, the data has no mode. The data has no mode. We can also calculate the mode for qualitative data, and I'll show an example later on. So what this is showing us here, there's two data values. Okay, two data values. These two data are almost the same, like they started with the same thing. They just cut off the largest value. Like, do you see how they have these large values? What happened to it? They rearranged on the other one. See, there's some values missing comparing the two data. So what they did, they found the mean for each one of them, and then they found the median and the mode. So the mode is okay, but notice how the mean for both data is larger than, like, the mean is larger than the median. Mean is larger than the median. So the idea here is the numbers, when we have a bigger numbers, as I showed you earlier, it affects the mean, but not the median. The median stays as is. So if we increase any number in the data by a bigger number, replace it, or by a small number, affects the mean, not the median. That's what this is about. Now, graphically, what this shows us, the first graph is skewed to the right. It's skewed right, the first one. If skewed to the right, then the mean would be to the right of the median. Mean would be to the right of the median, as you can see, because you're getting more, like, a bigger values or big value on the right side. That's why the mean gets shifted to the right. And the same thing in the last one here. If you get a way smaller value, then the mean changes and goes more toward the left. So the smaller you make the number, the smaller the mean. The larger the number, the larger the mean. If it's symmetric, then the mean and median are almost the same. Almost the same. Here it shows they're the same, but we say in statistic almost the same. Okay, that's what we call symmetric graph. It's a bell shape. And now we have what we call also, before we move on to computational part, what we call resistance measure. So we can introduce a definition, a resistance or resistant measure. The measure is not sensitive to the influence of a few extreme observations. So if I want to apply this definition to the mean and median, then we can say the median is a resistant measure of center. The median. The mean is not. See, read the definition again. It's kind of like backwards. Read it again and you will know. A resistant measure is not sensitive to the influence of a few extreme observations. That's what the resistant measure. And since the median is not going to be affected by the values that when we increase them or decrease them, that's why it's a resistant measure. But the mean get affected, that's why it's not a resistant measure. So the mean is not. This is these two information are good to keep in mind. So for the mode, let me also comment a little bit on the mode. So the mode can be used for both quantitative and qualitative. So quantitative, that's when they give you a set of numbers and you have to find it, the way I showed you earlier. Qualitative, how is that can be an example? Let's say they talk about chairs and color of the chairs and the number of those chairs from that color. Say red, white, black. Let's say we have 16, 22, and 17. What would be the mode in this case? Mode is the one, the number of chairs that is occurring the most, which is white. Right, for the white, which is 22. That's the mode. That's the mode. So even if you have it in this format, that's fine. Now, one thing important to know here, in a qualitative data, neither the median nor the mean can be used as a measure of center. Okay? Because we can't calculate the mean or median for qualitative data. We can only do it for quantitative data. Now, computational wise, we need to introduce some symbols. So the variable x gives you, these are the what we call them observations. Okay, observations. So if we have a set of data 2, 3, 7, 8, 10, 12, 13. Okay, so this is a given data. This is called x sub 1, x sub 2, those are subscript, x sub 3, x sub 4, x sub 5, x sub 6, x sub 7, just notations to represent each data. So if I want to find the mean for this, as we showed you earlier, you add them up all. So you add x1 plus x2 plus x3 plus x4 plus all the way to x7 divided how many entries you have. But instead of writing this way every time, we use x bar X bar. X bar means X with a dash on the top to represent the mean. And on the top, instead of adding all this every time, we can use the sigma notation. This is a capital letter sigma. Xi, X sub I. And then I ranges, you put here, I ranges from 1 to 7 in this case. 1 to 7 in this case. So if I want to do it in general, we go, if you have n entries, 1 to n. So this is sigma notation. Okay, and n is the total number of entries, number of observations, which we can call it the sample size. So again, given x1 is 2, x2 is 4, x3 is 7, x4 is 12. Find n, the sum of xi and x bar, the mean. N is how many numbers we have. They give us 4 of them. That's n. The sum of xi, it's how many we have here. I goes from 1 to 4. There's only 4 of them. So that's basically x1 plus x2 plus x3 plus x4. x1 is 2, x2 is 4, x3 is 7, and the last one is 12. And that gives us 1325. So that's the sum we were looking for. Now, if we want to find the mean is defined as the sum xi over n. Sum, we found it 25, and we have 4 of them. That gives you 6.25. 6.25. Easy calculations. Now the mean doesn't have to find the mean and all this stuff for just integers like this or whole numbers. It could be decimals, 1.6, let's say 0.4, 1.8, negative 0.2, negative 0.6, 4.5, 3.4, 1.2, 4.4, and 2.4. Let's say something like this. Now, the median, to find the median, you just arrange them in ascending order, and the middle one would be the median. Here we are interested to find the mean. So the mean, here how many values? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 of them. So the mean would be the sum of xi over n. Xi goes from 1 to 10 over 10. N is 10. And what does that give us? It's basically, this is the sum, x1 plus x2 plus da-da-da plus x10 over 10. And here would be 1.6 plus 0.4 plus 1.8 minus 0.2 minus 0.6 plus 4.5, all the way to the end of 2.4, all divided by 10. And then with the calculator help, we can put all these numbers in. Minus 0.2, 0.6, 4.5, 3.4, 1.2, 4.4, and 2.4. That gives us 18.9, and if you divide it by 10, it would be 1.89. That would be the mean. So if they give you fractions, decimals, negative numbers, positive numbers, they're all the same. It works the same way. Now we introduce another thing. It's called trimmed mean. After we found the mean, it's a trimmed mean. So sometimes I use trimmed mean when it comes to grading. So if you put on the Excel sheet the grades of all the students, and let's say a student didn't show up, and I mark it 0, it affects the mean. It affects the mean. So it will lower the mean for the class down. So to be safe, what we do, I just truncate that or cut it off, the smallest mean. And what we do here, the trimmed mean is used to improve the resistance of the mean. So usually how do we do this? We remove a percent of the smallest and largest observation, actually before computing the mean. So for example, if we have, as I said, let's say students scored 2%, 62%, 69%, 73%, 79, 80%, 80%, 88%, 89, and 99%. So I want to compute, so let's say we're asked to compute the 10% truncated or trimmed mean. So how do we compute trimmed mean? We remove, first thing, we remove the smallest and the largest two data sets. Then the mean, to find the trimmed mean, is equal to, you add the rest of the values, 62 plus 69 plus 73 all the way to 88 plus 89. We removed the other one. Now how many data values we have? In total we had 10, but now we have 8 left. So then if you calculate this, you get 77.5. One thing I want to let you know, when they said 10%, how do we do 10? Why did I move the first one and last one? Well, we have a total of 10. If I take 10% of 10, okay, just percent-wise, 10% of 10, 10% off means multiplication, cancel, cancel, so 1. So let me write it as a note here. 10% of 10 values is 1. So this means you have to remove the first one and the last one. What about if they say 20%? 20% means you do 20% of the 10 observations. Let's see, cancels, you get 2. This means you have to remove the first 2 and the last 2. So you remove the first 2 observations and last 2 observations before calculating the mean. Another note about this, trimmed mean is usually the best measure of center tendency for a data. Since what? When I truncated the zero was an outlier. Since there are no outliers, it's good. No outliers. We would always love to see no outliers in the data. Outliers affect the mean in the data. Okay, and the last thing to talk about, we started with this one. This is the sigma. If you have xi, I equals 1 to n, you just add them up, x1 plus x2 plus all the way to xn. Okay, so if they give me a set data 2, 3, 7, 8, 11, 13, and they ask me to find the sum of xi square. So how do you do this? Well, we have 2, 4, 6 of them. So this is the sum of xi. I goes from 1 to 6 square. So this is x1 plus x2 plus x6 all square. So you add these numbers up. 2 plus 3 plus 7 plus 8 plus 11 plus 13 all square. So we add all these numbers up, square, we get 44. And when we square that, we get 1936. Okay, 1936. So that's how we find the sum, the square of the sum of the values. What about if they ask us to find this? Find the sum of xi square. What's the difference? Well, this is, we have 6 values, so I goes from 1 to 6. So this is saying substitute I1, so x1 square, x2 square, x3 square, x4 square, x5 square, x6 square. So x1 square, x1 was 2. So you put a 2 here and you square it. The next one was 3, you square it. I think 7, you square it. 8, 11. So 8 square, 11 square, 13 square. So notice the first one, we had to sum up all, then square the result. Here, we square each one of them. Each one of them. Okay? And then we add them up. Then we add them up. Okay, so that gives us 416. Notice the two answers are not the same. 416 and 1936. So that's the difference between that one and this one. This one, we add all the numbers or observation, then square the result. Here we square each number and then add them up.